Alright, first question says, person on the surface of Earth has a weight of W, so I'll just write the W in there. What is that person's weight on another planet? Okay, I can't write W equals mg. I've got to write W equals, which is the force of gravity, g m1 m2 over r squared. Setting it equal to mg is only good on the surface of the Earth. So I'm going to change the changes that the question asks for. Has a diameter, planet which has a diameter 3 times less than Earth's. Okay, oh, you know what? I should have done that in another color to kind of show it. 3 times less than Earth. And a mass that's half as big. So I'm going to take one of these masses and half it. Now, what do the changes I did in red and the right do to the overall value of the fraction? So to keep the equality the same, I got to do to the left whatever I did to the right. I just half the mass. Halving the numerator has the effect of halving the value of the fraction. Making the denominator smaller actually makes the value of the fraction, or the denominator is getting smaller, makes the value of the fraction bigger. So if I'm dividing this by 3 and 3 is squared, I've got to square it before I take it out. So if I do that, I will then be making my denominator smaller by a factor of 9. Just do a little bit of reciprocal, multiply by the reciprocal, and you end up with it's 9 over 2, the weight. Okay, we're going around a bank turn. Radius r. I'm solving for theta. Okay. I'm going to take a look at this from this side. You have your bank turn looking like that. You have your angle theta there. You have the weight down, mg, and the normal force perpendicular to the surface like this. We don't tip our axes for bank turns. We keep a conventional coordinate system, and that's because that puts the part of the normal force that's actually going centripetally in our positive x-axis. So that would be n sine theta. Part of it that actually goes against gravity there would be n cos theta. So basically I'm going to transfer this down to here to show it more clearly. Now we got everything divided up into its components. Pulling up or pushing up, you got n cos theta. You're not going up and down on this axis, that's going to balance mg. And you've got n sine theta pointing inward. Okay. Now my y-axis, some of the forces are 0. It's not going up or down. It's just going around like this, around like this. So you can say n cos theta minus mg equals 0, or n, should be capital, cos theta equals mg. X-axis is my centripetal axis, so I got to say sum of the forces equals mv squared over r, and these are centripetal forces. There's one pointing in the circular path, which would kind of be like this. So you've got n sine theta equals mv squared over r. This point in time, I could solve, I got to combine to solve for theta, don't I? So this normal force and that normal force was the original normal force. I'm going to solve for it. N equals mg over cos theta. Bring that information over here. Combining my two sides, you get mg sine theta over cos theta equals mv squared over r. It's the same mass. We'll get g tan theta equals v squared over r. Divide over by g. You would get v, and then you take the inverse tan. You get arctan of v squared. Arctan of v squared over gr. This went through a lot of people. Okay. I gotta solve for the mass of the Earth. So we got this thing. If this is the Earth, this is something people miss out on a lot. This is the orbit of it. It said it was 2 Earth radii above the surface. That means it's actually 3 r between center of masses. So we have to use 3r for r when we do our math. So the whole time this is traveling around is one force on it, force of gravity, pointing centripetally inwards. So that is a centripetal force. So the force of gravity is mv squared over r. Except you're not on the surface of Earth. You're 2 Earth radii off of it. So you can't use that. You got to set it equal to g m1 m2 over r squared. So first thing to recognize is that the thing in circular orbit is this mass. So that's the mass that cancels out. What you're left with is the mass of the other thing, Earth. That's why you see, I don't see your answer solving for that. In the allowable terms, V's not allowed. It's not given. Oh, yeah, there it is. Solve for this. All right, I'm looking at all these things. They have no V in it. They got pi. So we got to change things up a little bit. Let's solve for the mass of Earth first thing. I can get rid of an r here and an r here if I just multiply through by an r. That would mean the mass of Earth, I'm just going to move over to the left, mass of Earth would be v squared r over, ooh, I fell for it, over big G. That's where I'm at so far. I see R's, I see G's in the answer. I do not see any V's, so I got to get rid of V. Now this is a uniform circular motion problem. So off to the side, I'm going to say V equals D over T. Traveling at constant speed, I could say that. I see big T's in the answer. Always look at your answers to try to tell you where to go. That's the time to go around once. That means the distance would be the distance to go around once. So that would be 2 pi r over big T, capital T. So now I'm bringing in the pi's and the T's, and it's starting to look like something. Okay? Let's get this information, bring it back over to here. So I've got mass of Earth equals, let's square it out here. It might be a little easier than to do it twice over here. So I want V squared, so that would end up being 4 pi squared r squared over t squared. Let's bring that in. 4 pi squared r cubed, because r squared multiplied by r again is r cubed, all over gt squared. All right, now that that's all done, last change you got to make is you are not 1 Earth radius away. You are 3 Earth radius away. All right, when we made that statement, we recognize that. I got to plug a 3 in for that. Making it specific to this problem. 3 times 3 is 9, right? 9 times 9 is 81. 81 times 4, what's that? 163.24. Oof. I didn't have that as an answer. Sorry. All right, 3 squared is 9. No. 3 squared is 9. 9 times 3, 27. 4 27s is 108. There we go. 108 pi squared r cubed over gt, and I'm not even in the picture. Right. All right, that's where I changed. I said, okay, let's make it specific to the problem. I made that 3r. 3 cubed is 27. 27 times 4, 108 over t squared. And there's your answer for that one. The last one, most people got right. All right. You've got off off the center of mass, just like always. Got T2 going that way. We got T1 going that way. 500 kilograms gives you a 5,000 Newton force going down. That's your load. Convenient coordinate system would just be standard one, because two of them fall on an axis. I only got to break one apart. That's 60. This would be T2 cos 60. Pulling up this way, which is the same as looking at it like this. You would have T1 sine 60. T1 pulls that way. T2, sorry, I don't know why I wrote a T1 there. It's T2. I'm breaking T2 apart. All right, my X, I got pulling to the left. T1, all right, remember this is a static equilibrium problem. It's not moving. So whatever's pulling left is pulling right. Whatever's pulling up has to be pulling down. So T1 has to balance T2 cos 60. And then in my y-axis, you've got T2 sine 60 balancing 5,000. All right. I can solve for T2 right over here now. T2 is going to be 1,000 divided by sine 60. Need a calculator for that one. All right. Clear that out. Let's go. A little rounding. Let's just do 5,000 divided by 0.866. Nope. 5, 1, 2, 3 divided by 0.866. 5,773 point yada 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 whatever, and then bring this over here, put it in there for that. You get 5,773 times cos 60, which is a half, and you would get 2886 pulling that way.